This program is brought to you by Stanford University. Please visit us at stanford.edu.
Let's go on from where we were. We were talking about how systems change with time. I want to go back over that since partly I don't remember where we were exactly. But second of all, it's always worth going over last week's material. It does not mean I don't have to make new notes. I always throw away my notes to make absolutely sure that I don't use the same notes twice. That's a very bad thing to do. Okay, but I do like to go over the material that we studied last week and just make sure everybody has it solidly. All right, so the state of a system is described by a ket vector, and we call it psi. Now, up till now, we've just thought of psi as a thing which doesn't depend on time. In fact, we haven't even talked about time. We did last week. But before last week, we didn't even talk about time. We just looked at the interrelationship between quantum states, observables, measurements, and that sort of thing. Now we want to ask how the quantum state changes with time. So we want to put a time argument in there. It's simply a vector which moves around in the vector space with time. The rule is that it moves around under the influence of a linear operator. And so we can write that psi of t is some linear operator which depends on time acting on psi at time 0. That's about the most general thing that we could write down. So far I haven't told you what u is, but it's the most general thing that I could write down under the assumption that state vectors change linearly. Now that's something that, as I've emphasized many times, I cannot give you a proof of. It's basically a postulate, but it's a postulate that's rooted in an experiment, plus the fact that anybody who ever tries to change it and do something different always winds up in some conceptual problems. Energy isn't conserved or something else, something bad. Probability isn't well-defined or whatever. So we'll take it as a postulate that the way systems change with time is through linear operators. Right? Linear operators just mean basically matrices, but matrices which are now time-dependent. Okay. We can apply the same rule, or the analogous or the related rule, actually the complex conjugate rule, to how bra vectors change with time. So here's some other bra vector. And this is basically the complex conjugate of some ket vector. And so we have to complex conjugate on the right-hand side, phi of 0. But then instead of u, we have to write the conjugate, u dagger of t. Remember what dagger means? From the point of view of matrices, it means you do two operations. You complex conjugate all the elements, and you reflect them. You transpose them about the diagonal. All right, so that's, these two rules are basically the same rule, one of them just the complex conjugate of the other. Now, the assumption about how systems change, you can express it in various ways. You can just express it as probability conservation, that the probability if the total probability is equal to 1, which it's supposed to be, then it should remain that way for all time. What is the total probability? The total probability is the inner product of the vector with itself, of the state vector with itself. And so we always write that physical, real state vectors satisfy psi equals 1, and we're not going to allow that to change with time. So that means that for all time, psi dagger psi, or psi conjugate psi, taking the inner product, should be unchanged with time. It's not hard to prove from that the inner product of any two vectors has to be time independent. That's rather easy to prove. I'll tell you how you do it. How would you do it for ordinary vectors? How would you prove for ordinary vectors that if the length of every vector stays fixed, then the inner product between any pair of vectors stays fixed. And the way you do it is you take any pair of vectors and you look at the difference of them. There's the difference of the two vectors. Now, if the assumption is that the length of every vector stays invariant, stays unchanged when you do some operation, some linear operation in particular, that means the sides of each one of these triangles shouldn't change under the corresponding operation. If the sides of the triangle don't change, that means the angle between these two vectors as well as the length of these two vectors doesn't change, and therefore the inner product or the dot product between them doesn't change. So from the assumption that the length of every vector doesn't change with time, the inner product with itself, it's also possible to prove that the inner product between any pair of them doesn't change with time. Right? If that's true, we can now write down a more general statement that phi of t inner product with psi of t is exactly equal to phi at time 0 times psi at time 0, if the inner product doesn't change. Okay, now plug in that phi of t and psi of t are related by this object called u, and so that becomes phi of 0, u dagger of t, u of t because that's what you do to psi, times psi of 0. So now we have a simple rule that phi of 0, that u dagger u sandwiched between any pair of vectors whatever is just equal to the inner product of the same pair of vectors without u dagger u. It's a simple elementary theorem that if the inner product of the matrix element of an operator is equal to the inner product for all vectors, then you can immediately conclude that u dagger u is just a unit operator. So the only way to make this happen is if u dagger u, for every vector, I mean the point is this is true for every vector in the vector space, the only way that can be true is if u dagger u is equal to 1. An operator with that product, a linear operator with that product, is called unitary. It's the analog for numbers, for complex numbers, of a complex number having unit length in the complex plane. Right? It's the analog of a number having the form e to the I theta. E to the I theta times its own complex conjugate is equal to 1. That's not what a unitary operator is, but it's the analog of that the operator times its Hermitian conjugate is equal to the unit operator. Okay. Then I think we derived this last time. I think we derived much of what I'm going to say today, but let's do it anyway. Supposing now, to get an idea of what u is, supposing instead of allowing time to evolve for a large amount of time, but let's just allow it to evolve for a very short amount of time. Now this is something that one is always doing in physics, studying how things change with respect to some parameter by chopping up the change into little infinitesimal pieces, and then studying how things change under an infinitesimal, under a very small change, and then building up big changes by superimposing, or what's the right word, juxtaposing lots of small changes. So we take the time interval, chop it up into a lot of little pieces, and instead of asking what u is for a finite amount of time, ask what u would be for a very, very small time interval, and then we'll try to build up what u should be for a large time interval. If we know how a system changes over every small time interval, then it should be possible to build up how it changes over long time intervals. Right? This is exactly, of course, the same logic as Newtonian mechanics, where you study the motion of a system by breaking up the time interval into little tiny segments and then deriving differential equations. So it's not a new idea, so we're going to take the time t to be small. T equals epsilon. That just means it's small. And the assumption is that epsilon is small enough that epsilon squared can be ignored. Standard small parameter approximation. Epsilon is small and epsilon squared is much smaller. So we ignore it. All right, now, if the time was equal to 0, for t equals 0, then u must just be 1. Why is that? Times 0 amount of time shouldn't change the system at all. If the system evolves for no time at all, it shouldn't change. And obviously, u should then just be the unit operator. The small correction should be proportional to epsilon. I'm going to write minus. And now this is completely arbitrary. I'm only putting in these factors here because I know that eventually I'm going to want to put them in. Minus I. Now the important factor is epsilon. A small change in time should lead to a small change in u. Times an object, which we'll call h. And now I'm going to put in all the factors that really belong, that would be there in the textbook. In the textbook, there would be an h bar, Planck's constant. Now, this is entirely conventional, meaning to say that there's no content in putting the I here, or the epsilon, or the h bar. It could all be absorbed into h, and then change the name of h and call it w. Yeah? So there's no content, none whatever, in putting this I and this epsilon and this h bar into the expression. It's just that for purposes of comparison with other things that were already pre-established by history, basically by history. It's more, it's got less to do with physics than it has to do with history. We put in these factors. The epsilon, of course, really belongs there. That you cannot get rid of because it's just telling you that the time interval is small. But other than that, everything else is pure convention. Okay, but using this convention, let's see what u dagger u equals 1 says. So we have to multiply, first of all, what is u dagger? U dagger is 1 plus I epsilon h dagger divided by, what is h bar? H bar is Planck's constant, of course. Anybody know what Planck's constant is?
6.6 minus 27 seconds.
Why is it such a ridiculous number?
Historical.
But what the, yeah, I know, but why, what insane person chose it to be such a, what history would make it so small, so ridiculous and...
Planck was fitting curves. Planck was fitting curves.
Planck was what?
Planck was fitting the thermodynamic curves.
Yeah, but why did the number come out so ridiculously small? Okay. Okay. Let's ask you another question. Why is the speed of light so big? No, yeah. Why is that a good one? Why is Avogadro's number so big? Yeah. It's because chemists wanted a unit that they could manipulate with their hands, okay? They had little beakers and other things that they put fluids into and gases. And how big were the containers? They were big enough to hold in your hand. They were big enough to tip over, to do things with. And so it was natural that the natural unit of measure of substance, in this particular case gases, should be the amount of gas that's held in a container about as big as a human being. Okay, maybe 50 times smaller than a human being, but that's all. Well, so the question then is a question not of physics. It has nothing to do with physics. It has to do with human biology. Why does it take 10 to the 27th atoms or something? No, it's more than that. 10 to the 30th atoms or whatever to make a human being? The answer is that with many fewer atoms than that, you couldn't make complicated enough circuitry and so forth to make an intelligent thing that can ask questions. So it's the peoplethropic principle that that if you weren't this big, you simply couldn't ask the question. So you better be that big. That's the reason that Planck's constant is small. It's the reason that the electron mass is so small. And so it really doesn't mean anything fundamental from the point of view of physics. It's just a choice of units. And it's a choice of units which goes back historically to a time when people didn't know about macroscopic physics. And so they worked with large, large numbers of electrons, large, large numbers of atoms, because they themselves were large. Okay, so h bar is just there because we're big. H is there because you got to put something there. The dagger is there because you have to take the Hermitian conjugate. The epsilon is there because we're talking about a small deviation from t equals 0. And the I is there because it will save me writing i's later on. Okay, you'll see in a moment why the I is there. All right, so what does u dagger u equal? We have to set u dagger u equal to 1. So that's 1 plus I epsilon h dagger over h bar times 1 minus I epsilon h divided by h bar. That's u dagger u. And then we ignore everything of order epsilon squared. And so the only thing that appears is 1 plus I epsilon h bar, h dagger over h bar. That's this term. And the other term is minus almost the same thing, h. The only difference between them is one has an h dagger and the other has an h. But our rule is that that has to be equal to 1. All right, so that being equal to 1 says I can cancel out the 1 on the left-hand side and set the result equal to 0. Another way to write the same thing, simpler, is just that h dagger equals h. That's the condition that u be unitary, that h be Hermitian. Hermitian means equal to its complex conjugate. Now, we've already argued, and you've accepted it, so there's nothing new, that observables, the things that you measure in the laboratory, correspond to Hermitian operators. Hermitian operators are observables are Hermitian operators. So, whatever this object is, h, it's an observable, according to the formal definition in quantum mechanics of observables. It's a Hermitian operator. It must correspond to something that you can measure. Moreover, it's got to be something very general. Precisely what its form is may not be general, precisely what operator, but every system has one of these. Otherwise, it couldn't change with time. So the existence of some kind of thing called h is very, very general. All systems have them. H is, of course, the Hamiltonian. The Hamiltonian means the energy. Thought of as an operator, it's called the Hamiltonian. Thought of as a quantity that you measure, it's called the energy. Okay? Sort of a redundant notation. We call it H, we could also call it E for energy. It's the same thing. We usually reserve the label E for the eigenvalues, for the things you actually measure, and H is the operator. Okay, now you can ask me why. Why is that the energy? Well, what other definitions so far do you have of energy? Anybody got any other definition of energy?
See, what's the classical? There's classical physics, which gives you energy.
Well, yeah, okay, what's the definition in classical physics? Oh, we're not, at the moment, no, that's not the definition of energy. That's most certainly not, that is the energy of a non-relativistic free particle, but it's certainly not the general definition of energy.
Capacity to do work.
What is work? Changing in the energy.
It's force times over distance. Force times distance, energy is part of it.
Yeah, we could work at it from that end, but to work at it from that end, we would have to work, that's a very special situation where you have non-relativistic objects, we have non-relativistic forces. The structure of energy, would that help you understand, for example, the energy stored in the electromagnetic field? Saying that it's mass times velocity or mass times velocity squared or whatever. No. There's some much more general concept. Right? There's a much more general concept, and one way of characterizing it is that it's conserved. That's the single most important thing about it, right? That it doesn't change with time. Right? And that for certain familiar systems, it takes a certain form. For certain familiar systems, it takes a certain form. Add that to the statement that the whole shebang, all kinds of energies don't change with time, the sum of them, and that's what energy is. So the most important thing that if we're just taking an abstract system and we don't know how to relate it to any particular non-relativistic classical system, the first thing we would look for in a definition of energy would be that it's conserved, that it doesn't change with time. We'll come back to it. We'll come back to it today. Why is this object an object that doesn't change with time? In what sense doesn't it change with time? We'll come back to it. Okay, so now we have an object which will give it its name. It's called a Hamiltonian. And we now know that the evolution of the system for a small amount of time is characterized by this expression here. Okay, let's see if we can make a differential equation for the change of a system with time. Why a differential equation? Well, if we know how a system changes over very small time intervals, it's natural to think of a differential equation evolving it from one instant to the next. So instead of looking at psi, let's look at the time derivative of psi, d by dt of psi. Well, that's equal, essentially by definition, psi of epsilon minus psi of 0. Incidentally, any time could be taken to be the 0 of time. There's nothing special about 0. It's just a small shift of time. T equals epsilon. The starting point was arbitrary. The important thing is that we change the time by a little bit. All right, so we've changed the time by a little bit, and now we have to divide by epsilon, and that's the derivative, the time derivative of the state vector. Okay, we have what psi of epsilon is. Where is psi of epsilon? Psi of epsilon is gotten by applying 1 minus I h over h bar. Psi of 0 is just gotten by applying 1. So what is this here? This is 1 minus, and now 1 minus I epsilon h over h bar. Did I get that right? No, I didn't. Psi of epsilon is this minus psi of 0. That just cancels out. The second term just cancels out the 1. So the difference in the numerator is nothing but I minus I epsilon h over h bar times psi of 0. That's the difference between psi of epsilon and psi of 0. Now divide it by epsilon. That just cancels out the epsilon. And that's it. That's another way to think about h. It's basically, apart from this factor of I over h bar, it's the operator which tells you how psi changes differentially with time, how it changes the time derivative of it. d by dt of psi is equal to this. Now that's great. That tells you how psi changes with time from instant to instant. It tells you the small change over any small lapse of time, or basically it's a differential equation for the state vector psi. This equation has a name. It's called the Schrödinger equation. You're probably not used to seeing it in that form. Anybody have a favorite form for the Schrödinger equation that we want to compare this with?
I like to spell it with the R first.
What's that?
I like to spell it R-O instead of O-R.
Schrödinger. Schrödinger.
You got Schrödinger.
HRO with an umlaut.
Yeah, umlaut, too.
Or he.
Yeah.
It's close enough.
Yeah, I think
It's within an H bar.
And that's it. That's all of quantum mechanics in a nutshell. If somebody tells you what psi is at time 0, you evolve it using the Schrodinger equation. You find it at a later time. You know the state at a later time. You make some measurements, and psi gives you the probabilities for all the measurements. That's it. That's the whole story. There's nothing else but that in quantum mechanics. This tells you how things change. We already figured out, if you know the state vector, how to calculate expectation values and probabilities and so forth, and that's it. Okay, but we don't want to just stop there. Let's try to solve this for some simple situations. Let's see. First of all, you know, there is another definition of energy that I'm sure you've seen before. It doesn't come from classical physics. It comes from Einstein and the photon. Anybody know what I'm thinking of? Hmm? Yeah, what's the formula? E equals h nu, right? E equals h nu. Or h bar omega. Omega, nu is frequency in cycles per second. Omega is frequency in radians per second. H bar is the thing that goes with omega. The other Planck's constant h is the thing which goes with frequency. Frequency times the old Planck's constant is equal to angular frequency times the new Planck's constant. Okay, you all know that. So let's see if we can understand why this h here might have something to do with this energy here. Okay? Let's see if we can figure that out. Let's solve the Schrodinger equation. But what I want to do is, since h is a Hermitian operator, it certainly has eigenvectors. In fact, every Hermitian operator has a complete set of eigenvectors. So there's some basis of states, some orthonormal basis of states, which are the eigenvectors of h. Let's imagine working in that basis. Okay? And let's pick one of the eigenvectors with eigenvalue e. E is the eigenvalue, so h on psi is equal to e times psi. Now, what happens if you start with an eigenvector of h? Well, I assert that it will stay an eigenvector of h with time, because if you wait a little bit of time, you'll be adding in, basically d by dt means just what are you adding in? What are you adding into to psi? You're adding in I epsilon h times psi. But since h times psi is proportional to psi itself, what you're adding in a little time interval is just something proportional to the original vector that you started with if psi is an eigenvector of the Hamiltonian. So if psi is an eigenvector of the Hamiltonian, it will stay an eigenvector of the Hamiltonian for all time, because the little things that you add in are pointing in the same direction. And if you add an eigenvector, if you add, you're just multiplying the eigenvector by a number. So let's look for a solution of the equation of the form, it's always the same. Psi now is by definition. This is, let me put a little e here to indicate that it is the eigenvector with energy e. Let's look for a solution of the form psi sub e of t is equal to, or just psi of t, is equal to psi sub e of 0. In fact, that's redundant. We don't even need that. Just some eigenvector of the energy times a function of time. Let's see if we can solve the equation that way. Okay, what is d by dt of psi if psi is just f of t times a constant vector? Well, if this is a constant vector, you just differentiate the f of t. So the left-hand side is, let's call it f dot. F dot means d by dt of f. Standard notation, a dot over something means you're differentiating with respect to time. All right, so f dot times psi, that's d by dt. And that's equal to minus I h over h bar times psi of 0, psi e. But h on psi e is just e times psi e. Did I leave something out? What did I leave out? Minus I e over h bar. So, Oh, I'm sorry, f of t. Yes, good. F of t. Very good. Okay, this suggests, or not suggests, it says that we can find the solution if we just find the solution of the equation f dot is equal to minus I e over h bar times f. F of t, the time derivative of f is just proportional to f itself. All right, now, this is not such a difficult differential equation. It says the derivative is proportional to the thing itself. We know how to solve an equation like that. Solution to an equation like that is exponentials. If you have an equation that says df by dt is equal to some constant, and all of this is a constant over here, a constant times f, then the solution to that equation is f is equal to e to the ct. If you differentiate an exponential, it just pulls down the coefficient of the time in the exponential. So the solution of any equation of the form that the derivative is proportional to the thing itself is an exponential. And now we can read off what the solution is. Here's the constant. F is equal to e to the minus I e over h bar times t. It could be a constant times that, but apart from a constant, the solution of f is this. Okay, we've now solved the Schrodinger equation. The Schrodinger equation, the solution, the time dependence of the Schrodinger equation for an eigenvector of the Hamiltonian is just to multiply by e to the minus I e over h bar t times psi of 0. Well, what is this here? E to the minus I e over h bar, that's a combination of sine, of cosine of I e over h bar t plus I sine I e over h bar t. So what is this? Frequency, omega. So what do we see? We see that f is e to the minus I omega t, where omega is equal to e over h bar. Now, suppose I hadn't told you that E was the energy. Supposing I hadn't told you before that H is the Hamiltonian and that E is the energy. At this point, we might look at this and say, ooh, I've seen that equation before. E equals h omega, h bar omega. This left-hand side must be the energy. From a quantum point of view and from the point of view of Einstein and photons and Planck and all that stuff, we would recognize the left-hand side as the energy. Not so clear that this has anything to do with the energy from Newtonian mechanics and so forth. But in order to study that relationship, we would have to be talking about systems which had a natural non-relativistic mechanical interpretation, and we're not at this point. So this is as close as we can get to a derivation for an explanation of why we call E the energy. It is the thing that Einstein would have recognized as the energy in this equation.
We have the cosine and the sine.
Yeah.
Should that be a minus sign?
Yeah.
And you don't want i's inside the
No.
sign. You don't want the i's inside the
No, I don't. Thank you. Right. Cosine E over h bar t minus I sine E over h bar. Right. But omega is equal to E over h bar.
When you wrote down the equation for h,
Yeah.
you sprinkled in some values like the h bar. You also sprinkled in the I there. instead of it all come out.
That's because, well, I sprinkle in the I so that the solution would be a Hermitian operator. Now, had I not sprinkled in the I would have found H dagger equals minus H. And I would have said, okay, that's an anti-Hermitian operator. That's called an anti-Hermitian operator. But I know what to do with that. If I take an anti-Hermitian operator and I multiply it by I, it becomes a Hermitian operator. So there was no content in it. I just put it there because I wanted I wanted to define the thing which would be Hermitian at the end. In other words, this is foresight or hindsight, I'm not sure which, but I knew the answer, and so I put it in.
And when you got down here, then E is going to be a real.
Yeah, and the reason it has to be real is because the unitarity. We don't want the length of the vector to change with time. You see, now we see it coming out that the length of the vector doesn't change with time. And that was ensured by having E being real. So I put all those factors there so that I wouldn't have to deal with them in the end.
That makes me think that equation E equals h bar omega came from studying electromagnetic waves.
Yeah. Well, it comes from studying any kind of oscillating system.
But is there some principle that says that the frequency of the electromagnetic wave is the same as the frequency of the quantum?
No. That's next term. Right. Right. Is there a principle? Of course there is, but nothing up until this point. No. The point being that E equals h bar omega is a more general thing than just photons and electromagnetic radiation. There's a more general interpretation of it, and photons being one special case of it. Okay, let's see. Supposing we have a vector which is a sum of eigenvectors of the Hamiltonian with different eigenvalues. In general, the different eigenvectors will have different eigenvalues corresponding to the different values that the energy can have, or that it can be measured. So supposing we take multiplying a vector by a phase like this is not very interesting. It doesn't change it in an interesting way. It just multiplies it by a phase. And we know that phases are not important in quantum mechanics. But supposing we have a vector which is some superposition of energy eigenstates. Now, the Hamiltonian is a Hermitian operator. It has a complete family, a complete basis of eigenvectors. So in principle, any vector, any state of the system can be expanded linearly in eigenvectors of the Hamiltonian. So let's do so. We start with the sum over n. N simply labels the different eigenvalues of, let's just write some coefficient alpha n times psi n, where psi n is the nth eigenvector of the Hamiltonian. Okay? What happens to that with time? Well, the point is that since the evolution is with a linear operator, we can figure out what happens to each psi and add them up. That's the nature of linear operators. That's the nature of linear operators, that you can bring them past the coefficients here and just figure out what they do to individual vectors, and it's added up in the end. So what happens to this? This evolves into summation of n, alpha n, but now we just have to figure out what psi n does. But we figured out already what each eigenvector of the energy does. It just gets multiplied by e to the I, e sub n minus I, e sub n over h bar t times psi n. Each one of the eigenvectors is evolving with a different frequency. This is quite different than an overall phase. Each phase of each component here is evolving differently. But that's the general solution of the Schrodinger equation. Each eigenvector of the energy just evolves with its own frequency. The high energy ones evolve very fast. The frequency goes around very fast. The low energy states evolve slowly. But if you break the system up into eigenvectors of the energy, then the solution of any quantum mechanics problem is just to write down that each vector. Yeah.
What you said, I mean, I could even classical mechanically, Fourier series is saying the same thing.
Well, this is a Fourier series in time. Yeah.
So I was saying even heat conduction, the higher frequencies evolve with higher, faster, and the smaller frequencies.
It's not. Normally, you would do a Laplace transformation for heat conduction, but you could also do a Fourier transform. Yeah, both make sense. Yeah.
So I was just generally saying, is there anything unique about this compared to?
Is there anything unique about it?
Because you are saying it from a Schrodinger equation perspective. So
Yeah. Well, I'm not sure exactly how to take the question. There's probably lots of situations where high frequency corresponds to high energy, but quantum mechanics being, usually it does trace back to somehow one way or another to the quantum mechanics, but I think we have to look at it case by case. It's a little too loose a question right now. Yeah. I wanted to do an example, but before I do the example, okay, that's all basic, easy stuff. In fact, everything is easy in quantum mechanics. What about observables? Observables, not the Hamiltonian itself, but other observables, other quantities that we can measure. How do they change with time? Okay. Now, what do I mean by how do they change with time? For the moment, let's ask how their expectation values change with time. Right? The expectation value, the average value, it's not, the average value of an observable. Let's call the observable A. The average value of A is psi A psi. Now, it's the psi's which change with time, not the A's. The A's are some very definite set of matrices that describe very, very particular observables. It's the states which change with time. I've given you the rule for how the states change with time, and that will allow us to figure out how the expectation value of observables change with time. It's only the states which change. So let's figure it out. Let's just ask, what's the time derivative? Well, first of all, let's call this A average. A average, and now I'm interested in the time derivative. I want to understand the time derivative, how the average of A changes with time. All right, we have a product of three things here. A state on the left, a state on the right, and a bunch of coefficients corresponding to the matrix A in the middle. How do we differentiate it with respect to time? It's just the product of three things. Two of them are time dependent, the size, and the A is not time dependent. Right? So we just treat it as a product of three things. Product of three things, how do you differentiate a product? Well, it's a sum of terms. In each term, you differentiate one of the factors, and you add them all up. So this then is equal to psi dot A psi plus psi A psi dot. No, I don't have to bother differentiating A. That's a fixed matrix corresponding to some very, very definite observable. And I fix it once and for all. I say I'm studying some particular component of the spin or whatever it happens to be, and I'm not changing it with time. The average only changes because the state of the system changes. Well, what do we do next? Anybody got a suggestion? Use the Schrodinger equation. Use the Schrodinger equation for psi dot. Okay. So what is this one? Let's look at this factor here, this term, psi A. And now for psi dot, I put in minus I h over h bar times psi. Do I have that right? Yeah. That's this term here. What about this term? For this term, I put in psi, but now the time derivative of the bra vector gets a plus I. I have to complex conjugate. So that gives me a plus I h over h bar times a times psi. Notice two differences in the two terms. In one case, I have a minus I. In the other case, I have a plus I. That's because I've complex conjugated. When I study the time derivative of psi, it's the complex conjugate of the time derivative of psi dagger. The other difference is the order of operation of A and H is different in the two terms. Here I have HA, here I have AH. Okay? Those are the two differences. HA minus AH. The factor I over H bar can be taken out. It's just I over H bar, I over H bar. Okay. Times psi HA minus AH. Psi. That's the time derivative of the expectation value of A bar dot, let's call it. We have a name for the product for HA minus AH. We've seen it before. Have we talked about that? Yeah, we talked about commutators, didn't we? We did.
Yes, you did.
Sure I did.
So I did.
But it doesn't matter because we could. Actually, I did. I proved the theorem for you that says that said that that two operators will have the same simultaneous eigenvectors if they commute. I do remember proving that, but it doesn't matter because it's just a definition. AH, take two operators. Let's call them A and B for a moment. The combination AB minus BA. In classical mathematics, if A and B are numbers, this difference is always zero, obviously. Okay, but they're not numbers. They're linear operators or matrices, and we know that matrices don't generally commute, that you can't interchange the order when you multiply them. And so this object, AB minus BA, is called the commutator of A and B, and it's written just a little square bracket with a comma. AB minus BA equals bracket, or not bracket, let's not call it bracket, let's not confuse it with bras and kets, but commutator symbol. Commutator symbol is the square bracket here. All right, so now we've derived a fundamental identity that the time derivative of any observable A, let's rewrite it now, A dot is I over H bar A bar dot is I over H bar times, now what is this? This is the average of HA minus AH. So it's the average of the commutator of H and A. So the time derivative of the average of an operator is related to the average of the commutator with the Hamiltonian. That is a fundamental significance of the Hamiltonian in physics, that if we want the time derivative of something, or the time derivative of an average value, that it is just equal to the average of the commutator with the Hamiltonian. Very simple. And where did it come from? Oh, because it's sandwiched between psi. Who asked me? Anything that's sandwiched between psi like this is an expectation value. Anything at all, if I want its expectation value, I sandwich it between psi. So in particular, the commutator is itself an operator, and I can ask, what is the expectation value of the commutator? And I've just written it as bar on top. So the time derivative of the average of A is the average of the commutator of H with A. Now, as the first application of this, let's do one simple application. I'm going to do two applications of this. I'll do one before we take a break and then one after we take the break. Question? Okay. What is the time derivative of the average of the Hamiltonian itself? Let's suppose now we didn't know what the Hamiltonian was. We had no idea what it stood for. It's some observable. We know that because it's Hermitian, but we don't know what its meaning is in the broader context of things. All right? So what is the time derivative of the average of the Hamiltonian? Zero. Zero, because the commutator of anything with itself is always zero. I mean, the mathematics of quantum mechanics is not so bizarre that that HH is not equal to HH. That bizarre it's not. HH is equal to HH. Okay? So if I plug in for A, H itself, I find out that the expectation value of the Hamiltonian doesn't change with time. Okay? Sounds like there's a conservation law. And there is. The conservation law is the conservation of H. Okay? Every system has an H. Every system has a conservation law. What more likely thing is there than the energy? And it is the energy. Okay, so Hamilton.
Question? Would there be a physical interpretation for the set of all matrices that commute with H?
Yeah. Well, it's the set of all things. Yes, good. It's the set of all things which are conserved.
And would that go beyond energy?
That depends on the details of the system. For example, if we have a particle moving in free space with no forces on it, then the momentum is conserved.
So, okay.
But if there's a force on the system, then the momentum is not conserved. So it depends on the details of the system, whether there are other conserved quantities. But yes, I mean, it's a good question. There is the collection of all things which commute with the Hamiltonian, and that collection is the set of conserved quantities, the set of things which are conserved for the particular system that you might be thinking about. Let's take a break. One other point that I forgot to mention. We're going to do an example in a minute. We're going to take all this abstract stuff and work it out in a very, very simplest case, namely a spin in a magnetic field, the simplest system that we know how to deal with. But we'll do it in a minute. But let me get all of the abstract things out, and then we'll do it in detail, in a concrete example. The Hamiltonian H is a Hermitian operator. That means it has a complete family of eigenvalues and eigenvectors. And if you work in the basis of states described by the eigenvectors of H, then H is a diagonal matrix. Right? Every H is a diagonal matrix in the basis of eigenvectors of H. That's trivial. Right? That's nothing new there. And so in the energy eigenbasis, let's call it, in the basis of states which are energy eigenvectors, the Hamiltonian is just a diagonal matrix E1, E2, E3, E4, and so forth, with zeros everywhere else. Now, we also saw what happened, where is it? We also saw what happened to an individual eigenvector as time evolves. As time evolves, each eigenvector gets multiplied by e to the minus I e h, or e over h bar t. That immediately tells us in the same basis, the basis of the same eigenvectors, it tells us what U is. U is a matrix whose entries are just these exponentials. Each eigenvector gets multiplied by this rotating phase, by this exponential, and the different eigenvectors don't get mixed up. Each one just gets multiplied. And so it tells us that the matrix in the same basis, is just e to the minus I E1 over h bar t, e to the minus I E2 over h bar t, and so forth, everything else being 0. The fact that the other elements are 0 means that the eigenvectors don't get mixed up with each other, that they don't rotate into each other. Each one simply gets a phase, and so it's a diagonal matrix that looks like this. The way this is usually written is just to say, well, these are matrix representations of linear operators. In terms of abstract operators, what one writes is that U is equal to e to the I minus I h over h bar t. You can interpret that just in terms of the eigenvalues, that the elements of U are simply the exponentials with a t here, appropriate t here, of the elements of H. That's a notation, if you like. Yeah.
So I have two different systems, and I bring them together, so I'm going to treat them as a single system.
Yeah.
But they each have energy components that happen to be at the same frequency. How do I interpret that relative to the fact that each eigenvector really is representative of a different frequency?
Oh, it may be, it can be that there are eigenvectors with the same frequency.
Okay, and so I just changed the coefficient. I just changed that eigenvectors. When I bring the two together, that value for that particular. Well, how would it change when I bring the two together? I don't quite see that.
I'm not sure what question you're asking.
So I have a Hamiltonian for each of two systems, and I bring them together to create a single system with a bigger Hamiltonian matrix.
Right.
If the energies in each of the two systems have the same frequency, when I bring the two Hamiltonians together, does that mean there's going to be some overlap in the two matrices? Okay, system A with Hamiltonian A and system B with Hamiltonian B. They both happen to have a frequency element that's common. When I bring them together.
Yeah, but remember, the frequencies of the combined system are the sums of the frequencies of the two systems. Yeah. 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 Well, no, it's not because it's linear. This is a separate postulate, if you like, that non-interacting separated systems which are non-interacting with each other have Hamiltonians which are the sum of the two Hamiltonians. Now, we could justify that, but since you asked me the question, the answer is that the energy eigenvalues are the sums of the eigenvalues of the separate system. Now, that's not surprising. Energies add. Of course, if they're interacting, that's not quite true. If they're interacting, that may not be quite true, that the energies quite add. But if they're not interacting and you take the combined system, the energies are simply the sums of the two energies. The Hamiltonians are the sums of the two Hamiltonians. Maybe we can even do an example if we have time. But I'm not sure if we will or not. But all right, the example that I want to do in some detail now is the problem of a spin in a magnetic field. Let's write down all the various equations that we need. Just a single spin now. No entanglement for the moment. Probably won't get to it, but so we have the spin matrices, sigma 1, sigma 2, and sigma 3. They represent the components of spin, and they're also proportional to the components of the magnetic moment of the electron, if it's an electron. And we have a magnetic field B. That's what we have. B, magnetic field pointing in some direction. It's a pointer. It's not we won't call it a vector because we get ourselves confused. But it is a thing that points in a direction of space, and it has magnitude B. The energy of a spin in a magnetic field is given by the product of the spin and the magnetic field. In fact, the dot product of the two of them. If you have a spin pointing in some direction and a magnetic field in some other direction, the energy stored is proportional to the dot product of the spin and the magnetic field. Or really, it's the dot product of the magnetic moment and the magnetic field. Now, the magnetic moment is proportional to the spin. If you have an electron spinning, the magnetic moment is proportional to the spin. And the what's the coefficient that connects them? Anybody know? Mu. Mu. It's called mu, right? Magnetic moment. The magnetic moment. So the magnetic moment, right? The magnetic moment, which is a little vector, is actually the spin vector times a number. The number is called the magnetic moment, mu. And I think there's a factor of 2 here in the definition. Let's not write that. Let's just write. Here's an interesting quantity. Mu times sigma over 2. The 2 is entirely conventional, and it could be absorbed into the mu. What is it? What is this thing? This is the thing that you multiply by B to get the energy. Right? Obviously, there's a little coefficient here that has to do with the charge on the spin. If the spin had no charge, there would be no electric current going around, and so it wouldn't interact with the magnetic field at all. So the magnitude of the electric charge of the particle is somehow buried in mu here, and this 2 here, I think, is just a convention. I vaguely remember there is a 2 there. I think there is a 2. In any case, the energy is sigma mu over 2 dot B, dot the magnetic field. So that must be the Hamiltonian. Let's take that to be the Hamiltonian, where now sigma is thought of as a quantum operator. B is just a magnetic field. It's got nothing. It's not quantum mechanical. It's just a great big magnet is sitting there, 10 Tesla magnet. B is 10 Teslas or whatever it is, and pointing in some definite direction that's provided by this big, heavy, stable magnet. We don't have to think about the quantum mechanics of the magnet. And so it's just there. Okay. Now let's choose B in a particular direction. What's the most convenient direction to choose? Let's choose B in the third direction along the z-axis. And then the Hamiltonian has a simple form. It's just mu over 2 times the magnitude of the magnetic field, just B without an arrow over it means the magnitude, times sigma 3. So this is the energy, or the Hamiltonian, of a spin in a magnetic field. Okay, what I want to calculate first is I want to calculate the time dependence of the averages of the 3 components of the spin. This is the analog of the classical mechanical question of calculating how the spin does whatever it does. Does it rotate? What does it do? Okay. So let's begin by calculating how the expectation values change with time. The expectation values of sigma 1, sigma 2, and sigma 3. First of all, what about sigma 3? Oh, let's write down the equation. The equation for the evolution of an expectation value is right here. Okay. So let's start with sigma 3. Sigma 3 dot. I won't bother writing expectation values. I mean here the expectation value of sigma 3, the time derivative of it. Okay. That's equal to I over h bar times the commutator of the Hamiltonian with sigma 3. But the Hamiltonian is just proportional to sigma 3. Okay. So the Hamiltonian, except for a numerical factor, is sigma 3, and the commutator of sigma 3 with itself is 0. So first thing it tells us is that the time derivative of the expectation value of sigma 3 is equal to 0. Let's draw. Let's draw. Here's the xy plane. Here's the z-axis, z, x, y. And now we've discovered that the component of the spin along the z-axis doesn't change with time. How much freedom does that give to the motion of sigma? Well, it means that the projection of sigma onto the third axis doesn't change, and it means that the angle of the spin relative to the vertical axis doesn't change. So whatever the spin does, the expectation value of the three components, it must somehow move on a cone of fixed angle here. Otherwise, the component along the z-axis would change with time. Okay, now what about the x component and the y component of the spin? That's more interesting. This one was boring. Basically, this was just conservation of energy, that this is equal to 0. That since the energy is proportional to the third component of spin, the conservation of energy must tell us that the third component of spin doesn't change with time, or the average of it. The average of the energy shouldn't change with time. Next, what about, let's see, which one did I do next? Yeah. Let's do sigma 1 dot. Sigma 1 dot is I over h bar times the commutator of sigma 3. H is, let's write down what H is. H is mu over 2 times B times sigma 3. So there's a mu, I over h bar times mu divided by 2 B times the commutator of sigma 3 with sigma 1. Now I'm looking at sigma 1 dot, so I write sigma 1 instead of A. The first entry here is still sigma 3. Anybody know what the commutator of sigma 3 and sigma 1 is?
I2 or something like that.
Okay, let's work it out. Let's work it out. Sigma 3, all right, so we're going to write sigma 3, sigma 1 first. First we'll do it in the order sigma 3, sigma 1. That's equal to 1 minus 1, 0, 0 times 1, 1, 0, 0. All right. Sigma 1 is here, sigma 3 is here. What's the product? Usual rule. First row times first column, 0. First row times second column, 1. Second row times first column, minus 1, 0. This looks sort of like sigma y, or sigma 2, except that it is lacking an I, right? This would be sigma 2 if there was a minus I and a plus I here. So this is actually 2I times, sorry, it's just I times sigma 2. Okay, let's check that. I times sigma 2 would be I times minus I, 0, 0. Minus I times I is 1. Yeah, that's correct. So that's I times sigma 2. Let's do them in the other order now. In the other order, we have 0, 1, 1, 0 times 1, 0, 0, minus 1. Okay, so now we have, let's see, first row times first column, 0 again. First row times second column, minus 1. Second row times first column is 1. Is that right? Yeah, 1 and 0. Now, this is the same as this except with a minus sign. So this is minus I sigma 2. But remember, when you calculate the commutator, you subtract these two. Subtracting minus I sigma 2 from I sigma 2 itself gives what? Twice I sigma 2. So the commutator of sigma 3 with sigma 1 is just twice I sigma 2. Let's write that down. Sigma 1 dot is equal to I over h bar, mu over 2, b, and then commutator of sigma 3 with sigma 1 is a factor of 2 I sigma 2. Now let's gather some stuff together. The 2's cancel. I think that's why I put the 2 there. I can't remember why I put the 2 there, but I think that's why I put the 2 there. I times I is minus. Now remember, these are expectation values. They're really expectation values. They're not operators. We could put a little bar above them. And being expectation values, the components are just numbers. So this tells me that the x component, or the one component of sigma, the time derivative of it, is proportional to sigma 2. And let me tell you what you get. Well, let's not belabor it. Let's just write down the answer. Sigma 2 dot looks very similar. Instead of commutator of sigma 3 with sigma 1, we'll have commutator of sigma 3 with sigma 2. And that winds up giving plus mu b over h bar times sigma 1. So we have the time derivative of sigma 1 is minus some constant times sigma 2, and the time derivative of sigma 2 is plus sigma 1. Does that look familiar?
Just a rotation. Just a rotation.
Yeah. Just a point rotating in a plane. Another way to say it is a very simple solution of this is to choose sigma 2 is equal to cosine of mu b over h bar t, and sigma 1 is plus the sign, I think plus the sign of mu b over h bar t. Do I have it right, or do I need a minus sign in there somewhere? The other way, yeah. This one should be sine. Sine. This one should be cosine. All right, derivative of sine is cosine. Derivative of cosine is minus sine. And when you take the derivative, you have to pull out the coefficient of t when you take the time derivative, and that gives you the mu b over h bar. So what this is, that means that in the xy plane, the component of spin in the xy plane rotates around like that. So the motion of the spin vector looks like a precession about the vertical axis. In other words, about the magnetic field. There's nothing special about choosing the magnetic field to be along the z-axis. We could have used any axis. Had I done so, we would have found that the component of the spin along the magnetic field doesn't change with time. That's energy conservation. And then in the plane perpendicular to the magnetic field, we would find it precessing around the magnetic field, just like that. That, of course, is also the known classical solution of the way a magnetic moment would rotate around a magnetic field, would precess around a magnetic field. It's kind of gyroscope is what it is. It's like a gyroscope.
Isn't there a phase factor in there in the solution of that sine sigma 1 equals sine plus the phase factor?
Oh, you mean for t plus a phase? Yeah, that's right. I mean, you can put in here, this is a solution of the equations. The phase factor simply corresponds, look down at it on the xy plane. There's a solution where at t equals 0, let's see, at t equals 0, only sigma 1 is non-zero. Let's call this 1 and 2. So we found a solution where the spin at time t equals 0 is along the x-axis and then it rotates. There's nothing special about t equals 0. And the way to indicate that is to realize that we could have started at any time with a spin pointing along the x-axis. And then we would put in here some minus theta, where theta would just be the phase factor or the time at which the spin was along the x-axis. Is that what you're talking about?
Yeah, but then I'm thinking, in order to do quantum mechanics, you've got to have millions of electrons, and they're going to have separate phase factors, so it's all kind of expectation value is going to be 1/2.
Say it again.
Since in order to do quantum mechanics, you've got to have many electrons to get averages.
Right.
And so each one has a different phase factor.
No. The point is, we're doing some experiment. We want to do the same experiment with all the electrons. All right, so what's the experiment? The experiment starts lining up all the electrons along some axis and then letting it go. So we pick an axis to line the electron up along, and then we let it go. If we're doing the same experiment to all the electrons, it means that we initially start them all the same way. Okay, right. If we have a system, you're perfectly right, if we have a system that nobody's been careful to start exactly the same way, but we just start them, right, then we have a mess. We have a density, we have a mixed state then. But if we start all the electrons identically, that could mean that we start, for example, we start them all pointing along the one axis at time t equals 0. Then they'll remain the same. They'll remain pointing the same way. Now, of course, sigma 1, sigma 2, and sigma 3 are quantum mechanical variables. What does that mean? For example, supposing we start the spins so that we know that they're pointing along the one axis at time t equals 0. That would tell us that if we measured sigma 1, we would get +1. If we measured sigma 2, we would get a half probability for it to be up or down. And if we measured sigma 3, we would also get a half probability. But let's start with a system along the sigma 1 axis and then let it go for a little time. After a little bit of time, the system is precessed into the 2 direction. That means after a little bit of time, if we were to measure sigma 2, we would find it definitely being up, but if we measured sigma 1, we would find it with half probability in either direction. If we wait another half period, or another quarter period, I guess it is, we would find the spin, if we measured along the x-axis, we would find for sure that it was minus, but if we measured sigma 2, again, we would find it randomly distributed. So that's the basic solution of the problem of a spin in a magnetic field.
If you had two electrons that were entangled, would that imply a 180-degree phase between them? Or I know you would, if you measured in any axis, if one of them is up, then the other is the opposite, given that they're started out entangled. Does that bear any?
What are we assuming about the 2 electrons?
You have two tangled electrons. If you measure one up, the other one is down.
Yeah. I know, but what are you assuming about the energy of the system? We can't say what they're going to do unless we have an expression for the energy. So one possibility is that there's no magnet around, but each one provides the magnet for the other one. Okay? All right. If that were the case, you can work out what the energy eigenvalues are and what the eigenvectors are. I'll tell you the answer. Okay. The answer is, let's...
Well, we're putting them in the magnetic field, unentangled them. I guess that's my first.
Say it again?
If you put them in the magnetic field, uniform magnetic field, would that unentangle them?
It might. If you put them in a strong magnetic field, it'll tend to line them up, but not necessarily, no.
If this is too complicated a question.
No. We could. It's easy to answer the question about 2 electrons when they're not in a magnetic field, but when they're providing a magnetic field for each other. All right. Then the Hamiltonian is proportional to the dot product of sigma and tau. Sigma 1, tau 1, plus sigma 2, tau 2, plus sigma 3, tau 3. Right. We know how the sigma 1s and the sigma 2s and the sigma 3s and the tau 1 and the tau 2 and the tau 3, we know how they act on the states, and we can work out what the eigenvalues are. There are 2 eigenvalues. The dimensionality of the space is 4. That means that there are 4 linearly independent vectors in the space. 2 times 2 is 4. But you know what the term is when there are equal eigenvalues for an operator for Hamiltonian? It's called degenerate. So if 2 states have exactly the same energy, then the energy spectrum is called degenerate, meaning to say that that there's more than one state with exactly the same energy. All right. This Hamiltonian happens to have 3 degenerate states and 1 state which is not degenerate with it. Okay. Therefore, there are 2 energy levels, and I'm just going to tell you the answer. You can work this out. The answer is that if both spins are, we can work in the basis where the spins are along the z-axis. If both spins are up, Then you have one particular value of the energy. Let's just call it equals E, meaning to say that it has energy E. If both spins are down, you also have the same energy E. And then there's two possibilities. Let's call it up, down, plus or minus down, up. One of them is the so-called singlet state. That has a different energy. The third, that's the minus sign. With the minus sign, let's call this E1, E1. With this sign, we get energy E2. But with this sign, down, up, we get energy E1 again. That's something you can check. That's why this triplet of states, up, up, down, down, and up, down, plus down, up, is called a triplet, and the other one is called the singlet. Right? So we have three different energy levels, and once you know there are three different energy levels and you know what the eigenvectors are, you can then expand any vector that you like to start with, pick anything you want to start with, which is some linear combination of these, and then just evolve it using the using the formula that we had on the blackboard, which seems to be gone by now. The formula that said you expand the states and eigenvectors, and each eigenvector goes with a phase that's determined by the right. What's the question? Well, right. You want to write down a general state? Pick a state. Pick a state to start with.
E2, the singlet.
Oh, that'll just stay E2, but it will have, that's right, it'll just stay that way. Any energy eigenvector doesn't do anything terribly interesting. It just rotates with its own phase. Okay? So what will happen to it is it will pick up a phase, e to the I, E2 over h bar t. But what's more interesting, let's see, supposing we just picked
Isn't the magnetic field going to supply some energy every once in a while?
at the moment, I don't have any magnetic field. No magnetic field. They provide, each one sees a magnetic field of the other one, that's all. Okay? So for example, we could start, let's do a problem. Let's suppose we start the system as up-down. That's not an eigenvector of the energy. I don't see among these, where are they? There's up, up, down, down, and up, down, minus down, up, and up, down, plus down, up. So let's actually work out what would happen if we started with up, down. That won't be trivial. We start with up, down. The first thing we do is we expand it in eigenvectors. Let's write down what the eigenvectors are. Up, up, down, down, and up, down, plus down, up, plus or minus down, up, divided by the square root of 2. Obviously, these two are not going to come into the game. It's these two which will come into the game. And in fact, I can write that up, down is equal to up, down, plus down, up. Put a bracket around it. Plus up, down, minus down, up. Divide this by 2 and this by 2. Okay, so up, down, plus down, up, and up, down, minus down, up. The down, ups cancel, and I just get up, down. Everybody see that? Okay. All right, now this here is square root of 2 times square root of 2, square root of 2 times square root of 2. Let's give these two guys names. Up, down, plus down, up, and up, down, minus down, up. All right? I have some names that I always call them.
Joe and Mary.
No. Seymour and Teresa. Singlet and triplet. This one is Teresa, the triplet. All right. So this is triplet divided by the square root of 2. Up, down, plus down, up divided by square root of 2 is triplet. Plus Seymour divided by the square root of 2. So that's the starting point. That's the starting point. Now let's evolve it for some time. There are two different energy eigenvalues. One of them goes with the singlet. Let's call this E triplet, and E singlet, E triplet. So what happens to this state as time goes on? The triplet state picks up a factor. Now I'm going to write down the state after a time t. This will become e to the I, E triplet, e to the minus I, E triplet over h bar t. Oh boy, we got too many t's, don't we? I better call Teresa capital T. Triplet, we'll use capital T. And what happens to this one? This one picks up the phase e to the minus I, E singlet over h bar t.
Which of ET and ES is bigger?
Say it again?
Which of ET and ES is bigger?
That depends on whether I put a plus sign or a minus sign in front of the whole thing. So let's see. If I have a plus sign, I think it probably for magnets you'd want a minus sign. The energy is typically bigger for the triplet state. That's when they're aligned, and when two magnets are aligned, you have more energy than when they're anti-aligned, right? Because they like to be anti-aligned. The North Pole likes to sit next to the South Pole, so they want to anti-align. That means it lowers the energy when they're anti-aligned, and that means that the singlet energy is less than the triplet energy. For example, we could define the energy by saying the singlet, you can always subtract a constant from the energy. That won't make any difference. We could set the singlet energy equal to 0. Then the triplet energy would be positive. Okay. Nothing actually depends on that constant, but let's just leave it there. Well, okay, now we have the evolution of the system in terms of the triplet and singlet state. But if we liked, we could go back to this representation. After all, I mean, the up and down spins might be the thing that we're interested in, whether they're along the third axis or not. These are both entangled states. I might want to write it in terms of unentangled states. So then I would simply put back, for the triplet state, let's see what we would get. We would get e to the minus I, et, t over h bar. Now, all over square root of 2. And now we would have triplet. So that would be up, down, plus down, up, over the square root of 2? Yeah, over the square root of 2. So that would be a 2 down here. That would be one component. And then the other component would be something very similar, e to the minus I, E singlet t divided by h bar over the square root of 2. That'll give me a 2 downstairs, and I'll have up, down, minus down, up. What do I want to do? What I now want to do is I want to pick off the up, down and the down, off separately from the two expressions and combine them together. I want to express this in terms of the particular states up, down, and down, up. So let's see what I get. What multiplies up, down? E to the minus I, et, t over h bar, plus e to the minus I, e, that's et, e singlet t over h bar, times up, down, over 2. Okay. But now what about the other component, the component with down, up? It's not quite the same factor. In fact, it has a minus sign, right? A minus sign from here. So what we get for the down, up is different than the up, down. Down, up gets multiplied by 1/2. You know, what is this here? 1/2 this times that? No, not quite. The ET and the ES are different from each other.
Yeah, hyperbolic. Oh.
Okay, I'll show you in a minute. No, it's not. It's not hyperbolic. It is e to the. It's obviously got to do with sines and cosines. What it is it's I believe e to the. Let's just leave it this way. Let's just leave it there. You can write it in terms of sines and cosines, but I'm not going to. E to the minus I et t over h bar minus e to the minus I es over h bar t. So you see that the up downs and the down ups get different coefficients. Okay? At time t equals 0, the coefficient of up down and down up are the same. At time t equals 0, is that right? No, that's wrong. Oh, no, sorry. At time t equals 0, we started with pure up down, if you remember. So at time t equals 0, this one's 0 at time t equals 0. Only up down. But then we wait a little bit. This becomes non-zero. This gets a little smaller than the fact. This one was maximum at time t equals 0. It gets a little smaller. This one grows and grows in magnitude. And after a little bit of time, you have a bit of down-up mixed in the state vector. So that means after a little bit of time, even though you started with pure up-down, after a little bit of time, you will have some probability of down-up. Now, you wait for a large enough time, and after a while, this one will cancel this one. There's a time at which this one cancels this one exactly, and at that time, this one is maximum. So it goes back and forth between up-down and down-up. Back and forth between up-down and down-up, sort of interpolating in between the two of them. That's what would happen. But you see the rule. The rule is first start with the basis that you're interested in, which happens to be, in this case, the up-down unentangled basis. Write the state that you want to start with. Re-express it in terms of eigenvectors of the Hamiltonian. And then take each eigenvector of the Hamiltonian, multiply it by the right phase, and then disentangle it back into the original basis. And that will tell you how the probabilities in the original basis change with time. Let's just see if we can simplify this a little bit. Let's see. I think this is e to the minus I et plus es. No. You know what the point is? What's that? No, you're wrong. No, you're wrong. You're wrong. Let me just see. What? Yeah, that's what I want to do. I want to pull out the average. Yeah. So, right. What I want to do, the average of the energy is ET plus ES over 2. I think that's what I want to pull out. E to the I, e to the minus I, et plus es over 2. Let me just think a minute. If ES had been equal to 0, then we'd only have this phase here. This one wouldn't change at all.
That's right.
Hmm?
Could call the average one was something like the cosine of the sine.
If you call the average, then you get e to the.
This is what you mean by the average. Yeah. Okay, so what we have e to the minus I et minus es t plus e to the I es minus et plus, oh boy. Yeah. Okay, this one's going to be cosine of et minus es. divided by twice h bar, right? Times t. And the other one looks exactly the same, has exactly the same factor, a phase, but then it has sign of the same thing, t. Now this is not important. This overall phase is not important. An overall phase doesn't mean anything, doesn't change anything. When you calculate the probabilities, the overall phase goes away. So you might as well just drop the overall phase. Forget it, it's not important. Do I have this right? Yes, I do. Okay, notice what happens. The probabilities only depend on the difference of energies. That's a good thing. They only depend on the difference of energies. The overall sum of energies doesn't make any difference. Only the difference of energies counts. And you can see what happens is that there's an oscillation back and forth between up, down, and down, up with a computable frequency here. Have I left something out? No. Notice what the frequency is. It's related to the difference of energies. So the difference of energies of the singlet and triplet state tell you how things go back and forth between the two states, up, down, and down, up. That's an example of a quantum mechanical problem worked out to death until it's finished. But the rules are always the same. Expand the vectors and the eigenvectors of the Hamiltonian. Let each one evolve with its own phase, and then put it back together again in whatever form you want to compute whatever probability you want. So it's a standard ritual. You reduce the problem to a ritual. Ritual is always the same. Okay, I think we're finished for tonight.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.